to the cloud and share my screen. And there we go. All right. So when we last met, we're going to just jump right in, my friends. Hold on. And what we're going to do is we're going to continue talking about fault geometry. So you guys remember we talked about foot walls and we talked about hanging walls and stuff like that. Okay. So what we're going to do is we are going to look at a bunch of different types of faults and get a feel for what they're telling us about the area or about what was going on in the area when we see the fault, where we can see the fault. So remember, we've got the hanging wall, the foot wall, and here is the fault plane. And it's important to know the difference between the hanging wall and the foot wall. This is why it's important, okay? We have three different types of faults. We have normal faults, we have reverse faults, and we have strike slip faults. Now, normal faults don't mean anything, that their name is normal, but that doesn't mean they're more common or anything. I don't know why they're called normal faults, but that is what they are called, okay? And in a normal fault, we actually have the hanging wall moving down relative to the foot wall. So one of the ways to look at this is to put your hands together. Oh, okay. Put your hands together like this. Okay. All right. So when you put your hands together like this, which one is the foot wall? Okay. The lower one is the foot wall. Which one is the hanging wall? The upper one is the hanging wall. When you move the hanging wall down relative to the foot wall, it slides down your hand. Okay. So everybody do that and get that feel. And I want you to notice what's happening to your elbows. Are they getting closer together or are they getting farther apart? They're getting farther apart, okay? So this is an extension. Anytime you have the hanging wall moving down relative to the foot wall, and I say relative because it actually doesn't matter which one moved. It's the relative motion to each other. So you could have the foot wall going up, you could have the hanging wall going down, or you could have both of them moving, and it still gives you that same relative motion. It's extensional. It means it's extending, it's pulling apart. Now, this pulling apart could be on the level of divergence. So there are divergent plate boundaries. However, there's lots and lots of places where pulling apart doesn't mean we're creating a new ocean or something like that. It's just the motion of the exterior of the earth, the crust of the earth. So, it makes a very distinctive set of, the topography is very distinctive around big normal faults. And we call these are mountains and valleys, and we call them horsts and grobens. Okay, so what happens is you have these undeformed layers, they're pulling apart from each other, and they create these very distinctive valleys and mountains, valleys and mountains, valleys and, well, okay, valley, mountain, long valley, little, so you get the idea, right? So this should make you think of our area. Okay, so our area has a lot of horsts and grobens. Okay, that's the name that is given to mountains and valleys. So mountain ranges and valleys that are made because of normal fault movement, of extension. And the reason why they call it this is, we've already mentioned this once in class, that a lot of geology words are German in origin. And because they were describing things, some of the earliest people were either English or German that were describing all of these geologic things. And so they've kind of stuck. So that's why we have schist and gneiss as rocks. And we also have horsts and grobens. The way to remember these is you get up on your horse, you climb up onto a mountain, you climb up onto a horse. Horsts are the mountains, grobens, you go down into the grave. Okay, so grobens, that's just the way I remember them, which one is which. But these horsts and grobens are what you see as you drive from Salt Lake City across down I-80 towards Reno. You go down and then up, and then down and then up, and then down and then up. And so this whole area has been extended. And it's really fun. If you look at a recreation of, say, what the United States looked like 50 million, 100 million years ago, it actually will show you if they're, oh, that's useless. Let's see if this one's any better. They'll show you, and Nevada will sometimes look like this. And California kind of looks like this because it's got this really weird things are going on out there that haven't been formed yet, the way we think of California. And even Utah is a little foreshortened because 100 million years ago, everything was squashed together and it has extended apart to make Nevada look like the way we expect Nevada to look like and things like that. So we live in a graben. So where you live right now, if you live in Utah County, if you live in Heber, up in what county is that? Wasatch County. If you live in Salt Lake County and in any of those places, you live in a graben. Okay, so let's concentrate on the one where BYU is. This is the Utah Valley graben. And as we go up on our field trip in 2 weeks, we're actually going to be going from the graben to the Horst. As we hike up that mountain, right at the very beginning, we're almost immediately on the Horst. So we live in the graben, we live in the valley, and you can actually see this. So here is the graben and here is the Horst. And that means that there is a fault right where the mountain meets the valley. And actually over by, I guess it's called Seven Peaks anymore, Splash Summit or something like that, where the water park is here in Provo. When they were starting to build some houses behind that area, they actually uncovered this huge part of the footwall. And we could actually go out there and measure it and stuff. And one of the cool things about this footwall is when it was first uncovered, it was all shiny and very, very slick. And that was because over millennia, thousands and thousands of years, it's been rubbing together as it has then slides and then it kind of grinds and then slides and then it grinds, slides. Every one of those slides is what? An earthquake, a fairly large earthquake. And that actually polishes the side of it. Okay, they're called slicken lines or slicken slides. It's kind of fun. It doesn't look like this anymore. People are built all throughout this area. It doesn't look anything like this, but this is the way it looked when it was first uncovered. Those are normal faults, okay? So let's talk about reverse faults. Reverse faults are the opposite of normal faults, okay? The hanging wall, you put your hands together again, the hanging wall moves up relative to the footwall. That means your elbows are getting closer together. Your wrists are getting closer together. So this is a compressional action, okay? It actually pushes things together. And so it shortens things. It makes it thicker and shorter. So not only are we getting closer together, but we're piling all that stuff that used to be stretched out all together, and that actually does make it thicker, which makes sense. Now, in thrust faults, there's actually a special, with reverse faults, all of these things that we're talking about are reverse faults in this little section, but there's a special kind of reverse fault called a thrust fault. And that is a low angle reverse fault. And those are actually really quite, they take up, they're very large regionally. They're a regional kind of thing. And what they do is they actually thrust old stuff over new stuff. Remember the law of superposition, the principle of superposition that said that the oldest stuff is always where? At the top or the bottom? At the bottom, right? Well, imagine if you're out there, you're hiking around, and all of a sudden you find fossils that are older on top of fossils that are younger. You're like, what the heck? Well, remember, one of the things about the principle of superposition was that they had to be undisturbed, undeformed, unmodified layers, because you actually can stack older stuff on top of younger stuff, and that can get very confusing until you go and you figure out what's going on. So let's just look at some things about that. So the Keystone thrust, how many of you are from Vegas? Do we have Vegas people here? Whoop, whoop. Okay, Red Rock, okay? Red Rock itself is part of this Keystone thrust. And what happens is this stuff back here, this is a bunch of Mississippian and Pennsylvanian limestone, okay? And this is Jurassic. So we're talking, this is Paleozoic, and it's above Mesozoic stuff. And that's backwards, right? Because Paleozoic is older than Mesozoic. Same thing happens here in Davis County. Anybody here from Davis County? Okay, woo, woo. Okay, we got Davis County. And we have what's known as the Willard thrust, and it's older stuff that has been squashed over younger stuff. So this darker stuff here is younger than this lighter colored thing. Okay, so those are some of the examples of these thrust faults that are low angle, and so they go over lots and lots of areas. So you can have a reverse fault that is really, really almost horizontal. and it's just sort of over long distances will just creep over. In this case, what you're thinking about is you've got, okay, so imagine the bottom of my arm is older rock and the top is younger rock, okay, both sides, okay, we're just regular normal old rock, right? If I do a thrust, so here's my hanging wall, here's my foot wall. If I do a thrust, eventually I'm going to get over here. And now what I've got is I've got my older rock touching my younger rock in distances. So you don't often, sometimes with thrust faults, you can't really find the thrust bottom sometimes because it's harder to see, or it's you know, it's not exposed or stuff like that. But as soon as you find that older stuff, you're like, something's going on here. I need to figure it out. And then you go look for it. Turns out that running rocks across each other, just like with the hanging wall that we saw, the foot wall that we saw in Provo by the swim park, it gets all polished and everything. That actually can be so strong. Those earthquakes can actually crumble the rocks and actually fuse them and burn them and melt them. It's called a cataclastite. You don't need to worry about that word, but what it is you go look for that little part. You're like, oh, there's a fault right here. And this is why we've got this weirdness going on. So it can get very complex. Other questions? Okay, now let's talk about strike slip faults. Strike slip faults are pretty cool, okay? Who here has heard of the San Andreas fault? Okay, the San Andreas fault is a strike slip fault. Now, do you guys remember what strike meant? Oh, what was strike? Talked about that on, it's the compass direction. So it is the direction that the thing is trending. If you have a road that goes north and south, you know, then the strike is north-south. That's what the road is. So I-15 is roughly has a strike of north-south. So if we have a strike slip, that means instead of slipping on the dip, it's slipping along the sides. So it's slipping past each other. The principal movement is not up and down, it is horizontal. So it's usually related to transform plate boundaries, okay? But it doesn't have to be, but it usually is. Okay, so little or no vertical movement. So when you have this fault, they're going to be moving like this, and there's almost going to be no up and down. And the way we classify strike slip faults, so normal faults, they're just normal faults. If the hanging wall moves, I always have to say this the right way. If the hanging wall moves down, it's a normal fault. If the hanging wall moves up, it's a reverse fault. With strike slip faults, though, we have two different directions they could go, and that's called right lateral or left lateral. And the reason why I have this right here, abrupt changes in drainage patterns, is because this is one of the main ways to see it. Because you are just sliding past each other. It's going to be, you've got the same layer the whole time. So it's going to be really hard to be able to see that you've got this fault going on. But if you're looking at drainage pattern differences, then you can start seeing it. And to illustrate that, let's look at this top one right here. So before this fault began moving, we actually had this drainage, this river, this stream, and it just would go straight. But every time there was an earthquake, this part of this side of the fault moved down this way. This side of the fault moved up this way. But the drainage pattern is going to try to follow that because this has already all been incised. It's very comfortable for the water to go into. It's the lowest part in the area. Water always goes downhill, that kind of thing. So it actually does these weird disrupted drainage patterns. And to give you an example of that, this is what we're looking at, okay? So this drainage pattern, and then it moves over, right? Okay, so what happened is well, which way went which? So when you're looking at a strike slip fault and you're trying to figure out if it is left lateral or right lateral, this is what you have to do. Imagine yourself, do I have this anywhere? Yes, I do. Okay, that's what I thought. So, all right. So when you look at this, which one moved which way? Which one moved to the right? So if this is the fault, the top or the bottom moved to the, I have to look at this the right way. So I'm, move to the right. Which one moved to the right? The top did, right? So the top is moving this way and the bottom is moving this way. So this is a right lateral fault. So right lateral versus left lateral, the best way to look at that is imagine yourself standing on one side of it and looking over to the other side of it. Imagine yourself standing on one side of it and looking over to the other side of it. Which way did the side on the other side? So you've got your fault on the other side of the fault. Which way did that move? So if you're standing right here and you're looking this way, to make these things match up, you notice that this side moved to the right to get it to look like this. Does that make sense? And it works for both directions, okay? So if you were to stand on this side of it and you were looking across, the other side has moved to the, oh, sorry, yeah, did I say right? I should have said left, sorry, this one's the left lateral. Does that make sense, or have I massively confused everybody? Everybody's okay, okay, good. Whew. Well, then let's do this one as a participation exercise. All right, guys, here is the queen fault, something like that. And so I don't pronounce things. So, okay, is this a left lateral or is this a right lateral fault? So I have everybody who thinks that it is a right lateral fault, raise your hand. Everybody who thinks it's a left lateral fault, raise your hand. Everybody who's not sure what the heck I'm even talking about. Okay, a couple of people, and that's totally okay. So what I want you to do is I want you to imagine yourself standing at this star and you're looking across the fault. As you're standing there and you're looking across the fault, I guess I should go this way because that's the way you guys are looking across the fault. And you know that you've got, say, let's look at this green bed, this kind of cool green bed right here. And we can see it on both sides. Which way is the green bed? So the green bed is on your right here. Which way is it on your, across the thing, across the fault? It's on your left, right? And so that means this is a left lateral fault. If you kind of reconstruct it, put it back to the way it was, so it was all just one line, and then which one had to move which direction to make it look like it did today. Does that make sense? Hopefully. Okay. All right. How about this participation quiz? This is not a a strike slip fault. This is either a reverse or a normal fault. Which one is it? So which fault block is the hanging wall? And then if the red stars indicate the same layer, so this was all one continuous layer at some point, which way did the hanging wall move? Okay, turn to your neighbor and talk about it. Figure it out. Okay. All right. Which fault block is the hanging wall? One or two? Two. Does anybody want to talk about that some more? To make sure you feel good about picking out which one is the hanging wall. Okay, let's do that. All right. Do you want to ask a specific question or do you just want me to explain it again? No, that's totally okay. Let's talk about it because it's the reason why this is an important thing for you guys to understand is there are certain parts of geology that you can't do when you're just wandering around hiking, okay? You can't figure out what the chemical composition of something is. You can't, most of us aren't ever going to be so expert at looking at fossils that we can be able to tell exactly what age something is, right? So understanding the things that we can tell without having any extra knowledge or laboratory experience is important so that you can actually look at it. So this is why we care. Okay, that's why we care. So to be able to figure out which one is the hanging wall and which one is the foot wall, let me draw this. So here is the fault. Here is number one. Here is number two. And let's just pretend in our minds that we have now separated these so they have a space in between them. Okay. Hello? Okay, that's weird because I'm the only participant today. So that is kind of strange. Okay. So now we just like have separated it like that. And once we've separated it, then we could like pretend that we're climbing up into it. And where we could actually climb is the foot wall, and where we would have to hang like Spider-Man is the hanging wall. Okay, so when you do that, every time you look at a fault that is a vertical fault that you're seeing in a vertical space, a cross section of it, just separate it and then say, which one would I be hanging off of? Which one would I be climbing up? And you'll be able to do that. So hopefully we'll do a few more examples. So hopefully that'll make some sense. So if the fault block, if number 2 is the hanging wall, then is the hanging wall going up or going down? Okay, who votes for down? Who votes for up? Okay, all right. So I feel like that we've got this, okay? Pretty good, right? So this is a normal fault. It's a normal fault because remember that the hanging wall moves down in a normal fault. Okay, so we know that this is an extensional, that there's been extension in this region. It tells us something that was happening in the past in this area, that it was extending, it wasn't compressing. All right, now everybody take a moment and admire his awesome pink shorts. And okay, now figure this one out. Which one is the hanging wall? Which direction is it moving? Talk to your neighbors.
I see. No, you're right. I see the next one. I didn't forget.
Okay, all right, you guys, which one is the hanging wall? Number 1, good job. Okay, which one is, so is the hanging wall going up or going down? So what kind of a fault is this? So again, it's a normal fault. Yes. Now that happens, and that is a pain in the neck. Okay, so fortunately, it's not super common. Okay, so in one area, maybe that's the way to look, but then as you go exploring more, you'll be able to find a place where it is on an angle more. But yes, that does happen. And you don't really call it, you just say, hey, there's a fault here, something's going on, and I don't have enough information to figure out which kind it is. And then you have to go out and do more work, so generally speaking. Okay, once more. Remember, tell me what the hanging wall is. Tell your neighbor what the hanging wall is. Tell us if it's a normal or a reverse fault, or in other words, is the hanging wall moving up or down? Okay. Okay, what do you guys think? Which one is the hanging wall? 2. And that means this is a reverse fault because the hanging wall went up relative to the foot. How you guys doing? You feel like that makes a little bit of sense? If I gave you one of these on a test, you could figure it out, right? Okay, I'm actually going to pass around a rock, a clever little rock that I found up in the mountains one day. And it actually has a fault in it. It's a little tiny rock that has a fault in it. So what we're going to do is I'm going to pass it around, and I want you guys to just kind of look at it for a second and decide what type of fault it is. Okay. All right, we're going to start with Chelsea and Miriam, and you just look at it quick and then you move it along. Okay. All right, so that's faults. Okay, remember faults are which kind? Brittle or ductile? Deformation. They're brittle deformation. Remember, they snap apart. They're actually breaking. Now let's move on and start talking about ductile deformation. And remember that ductile deformation is, generally speaking, very slow and usually needs to be warm. Okay, you need to have some kind of heat involved with it. So rock layers can be warped. All right, so think of a blanket. When you're pushing together the edges, it's going to become these cute little waves in your blanket. And this is due to ductile deformation, but more specifically, almost every time we see folding, it has to do with compression. Okay, so you are almost never, in fact, I don't know of an example where you actually see folding happening when you have extension. It is always compression. It is always coming together, convergence of some type. Now, just like when we're talking about extensional faults, and I said that we find these in divergent plate boundaries, but finding one doesn't mean that it's a divergent plate boundary necessarily. Okay, the same thing is happening here. We have convergence happening of some kind. We have compression, things are coming together. That doesn't always mean that we're at a convergent plate boundary. It could be other things that are going on. So so whenever you see these folds, you should be thinking compression. You should be thinking convergence, things coming together. We've got the rods right there. Yeah, okay. And the really complex thing that can happen is you can actually end up with a ton of them. Here's one set of folds, and then sometimes, then another set of folds comes in and like complicates the first set of folds. And then you have another one and another one. So you can have multiples of these. And the way we classify these, we of course, because we're scientists, we have to name everything. We classify these based on, this is going to be like, crap, what is she talking about? But don't worry, it's going to make a lot of sense. Strike of the hinge line, the dip of the limbs, and this gives us anticlines, synclines, monoclines, etc. So you're like, crap, I don't know what she's talking about. So basically what the hinge line is you find a fold. We're going to use a hymn book, because why not? You find a fold, and the hinge line is, can't really do this very well. I don't have enough hands, but the hinge line is where on either side it starts going in a different direction. So the hinge line is down the middle. You slide down one side, you slide down the other side. Same thing if we did it like this. Hinge line is in the middle. You go up to one side, you go up to the other side. Okay, that's the hinge line. Okay, so is it going down? Is it staying horizontal? Does it even have a hinge line, or is it on all sides and stuff like that? And then the dip of the limbs. Do the limbs dip down? Okay, so that you slide off away from the middle, or do the limbs dip up so that you slide down to the middle instead of sliding away from the middle? Okay, and that is how we're going to be able to say what our anticlines and synclines and everything like that are. So a syncline is a warp downward. The dip is towards the middle. So if you were to be able to slide down this guy, you'd sit right here and you'd slide down to the middle. This is called sidling hill, and it is in Maryland. What do you think? Pretty sure it's in Maryland. It's really, really, really cool. They actually have a geology park that's just right behind here, and you can kind of look and see why this was the way it is. But this area is in the Appalachians, which is one of those folded mountain belts that we've talked about. And this is why it's folded. Like, you remember, we had all of that compression happening when we had convergence, and we had really tall mountains as tall as the Himalaya. That's what the Appalachians used to be. And then now it's just been all the way eroded down to those roots. So a syncline dips towards the middle, and the strike is horizontal to the ground surface. So it's not like going in or going up, it's just plain horizontal, okay? And it makes a smile or a U shape. So syncline, smile. Pretty easy, right? Okay. And in this case, when you have a syncline, your youngest layers are always in the middle. So if you can imagine that, you look at this, here's the shape of the syncline, but as you're walking across this, it's practically flat. So how are you going to be able to tell which way everything is dipping? Well, you could measure all the dips, or you could look and see which one is the oldest and which one is the youngest beds. And the youngest beds in a syncline are in the middle. So unfold this in your brain, and that makes sense. The oldest is going to be on in the bottom, and so that means it's on the edges, and the youngest is going to be in. An anticline is the opposite. It makes an A shape, anticline A shape, pretty convenient there, okay? It warps upward, and that means that if you were able to slide down this, you'd slide away from the hinge line, okay? And in this case, the oldest layers are exposed in the center. And that's because if you can imagine with me, so if I were to say this layer here, well, let's do this layer here and this layer here. Okay, which one's older, A or B? Which one's older? A or B? Just so A is older because it's farther down. If we just looked at these layers, okay, it's farther down, right? And now imagine if you sliced off the mountain right here, you would have your older beds in the middle, and on either side of it, you would have your younger beds. So can you see that with this? How this used to be projected up, but it's been eroded, and now you can see that the older bed, this bed, is in the middle, and the younger bed is on the sides. Monoclines are kind of weird, and they only dip in one direction. Okay, so they are like one side of it. So you don't actually know, is this the syncline? Is this an anticline? No, it's neither, because it's only got one limb. So it's a monocline because mono means one. And so this is a case where we had all these nicely horizontal rocks, and then whoosh, they just dip down, and then they just go back to normal down over here off the picture. And so this is a monocline. So you can't say that this one's a syncline or an anticline because you only have the one limb that's doing it. Now, unsurprisingly, a lot of times you're going to find anticlines and synclines together. Okay, so you'll have, well, is this an anticline or a syncline? Yes, it's both, right? So here's the anticline, but then this same limb of the anticline is part of the syncline, which is part of the anticline here, which is part of the syncline here, but when sometimes we get really broad ones, the only ones that are exposed are the ones, for example, that you can see here. We don't actually see the anticline on the other side. It's eroded away. It's not visible. Maybe it didn't happen, whatever it is. So you do find them by themselves, but you also find them all together. Now, the last thing of this type that we're going to introduce you to is domes and basins. And what domes and basins are is when you actually, it's really hard to do with like paper and stuff, but it's like if I could force this all around my fist and it would make a dome. So basically it's a bowl, okay? And this is really gently warping, okay? So this is just really, it's not very steep or anything like that, really broad areas. And they make these roughly circular patterns, okay? And so these domes and basins, usually you will see anticlines and synclines closer to wherever the compression is happening. And then farther away, you're going to see these domes and basins. So that means it's a more gentle stressor, more gentle stress that's hitting it. And so the way to tell the difference is, well, if it's a dome, it's going to be like an upside down bowl, right? And that means everything is going to dip away from the middle. And if it's a basin, everything is going to dip towards the middle. So it's like a regularly shaped bowl. But a lot of times it's really hard to tell which way something is dipping. Maybe you don't have very good exposures. Maybe all you have is a satellite picture and you really can't tell what the dip is. Then you're going to start looking at, can you tell which one is the oldest strata? And in a dome, the oldest is in the middle. It kind of makes an A shaped, but it makes an A shape on all sides. And in a basin, it makes a smiley face, and the youngest strata is in the middle. So they do correlate with each other. Synclines and basins, domes and anticlines. There's this really cool structure in the Sahara Desert in Mauritania. It's called the Rikat structure. And when people first saw it, it's in the middle of nowhere. So nobody saw it until we had planes. Okay, so then we had planes and we have World War II and people are like in the Sahara because that's one of the fields That's one of the theaters of war is the African front. And they're flying over it and they see this giant bullseye in the ground. And they're like, dude, what is that? And so for a long time, people thought it was an impact structure. So it was like a meteor came down and whacked into. And then when people actually first got out there, they now know that it is a structural dome. It's actually a dome that has been worn away. And so if it's a dome, tell me the age of the middle compared to the age of the outside. Older, because domes have the oldest rocks in the middle, okay? Now, finally, we can take any of these, anticlines, synclines, domes, monoclines, whatever, and we can make it so that they're not parallel to they're not horizontal to the ground. So all the ones we've talked about them being horizontal to the ground, but really that doesn't happen very frequently. Most of the time, you're going to have a slight tilt of some direction, and we call those plunging folds. Okay, so that means that the fold axis is going down into the ground. So instead of being like this, it's like this. Okay, so it's plunging into the ground. And this makes some really cool structures when you're looking at it from space or in a map view, or when you can just see stuff that's going on. And we call these, so a plunging anticline. How many of you guys have ever been to Quail Creek Lake in St. George? Okay, so Quail Creek or Quail Creek, which was the way my dad always pronounced it, is in the center of an anticline, a plunging anticline. And so what it looks like is it actually starts to look, instead of just looking like just parallel lines to each other, the lines actually start to converge on a point, and it looks more like this. So it's not a bullseye, but it's like an arrow kind of a thing. And so can you kind of see that shape? Can you reconstruct it as an anticline here? You can definitely see the anticline here, but everything is all going into the picture. So everything is plunging down this, okay? So that's the more common thing. You really generally don't see them perfect, all right? All right, let's talk about the homework assignment that was due this morning, okay? The reading assignment. What did you guys think? How did you guys do? Who got all of them right? Hey, good job. Who wants me to talk about them? Couple of people. Okay, let's talk about them then, okay? So while looking at a map, you notice an area that looks like this. And luckily for you, it has strike and dip. I mean, it's got your dips showing you, and it's showing you the ages. So what did the area look like before it was eroded? Because now it's completely flat. Before it was eroded, did it look more like A or did it look like B? Well, there's a couple of ways you can look at this. First of all, you could look at the ages and say, okay, I remember that anticlines have the oldest in the middle. So now I just look at this and say, is the oldest in the middle? No. So this is a syncline. This has to have been a syncline. Right? Okay, but the other thing you can also look at is you can look at which way it is dipping. So all the arrows are showing you the dip direction, and it's dipping towards the middle, which means that it's a syncline once more. And then the last thing you can do to answer a question like this is to just look at this and see if it makes sense if I unfold it. If I undome this thing, if I unmake this into an A shape and make it flat, does it make sense to have the youngest one on the bottom? It doesn't, okay? Geologically, that doesn't make sense. So we would then select B. That's what. So there's 3 different ways to figure that out. So, so this was a syncline. So what if the striped rocks had ages and dips like this? So if it looked something like this. Well, once again, are they dipping away? If they're dipping away, it's an anticline, dipping away from the middle. The oldest is in the middle, and that is an anticline. And once again, you can unfold these and see if it makes sense for it to be a syncline, or does it make sense for it to be an anticline? And of course, in this case, it makes more sense to be an anticline. So if I were to ask a question on a test that actually had something that looked something like this, or something like this, or maybe in a dome or a a basin, so it looked more like a bullseye, you could answer that question without breaking a sweat, right? Hint. Okay. Whoops. All right. So for the last just couple of seconds, I want to just talk about, what did you guys think about my rock? Is it a normal fault or is it a reverse fault? Who votes for normal? Who votes for reverse? Who doesn't have a clue how to figure it out? I didn't get very many votes. So okay, does it or does it? Okay, let's talk about that. Okay, I'm going to turn on the light because that is something that I used to have a really hard time with. So that's why we're going to spend some time talking about. Okay. All right. So I'm going to draw the rock in two perspectives. So looking at it this way, here's my rock. Here's my fault. Here's my vein. This is a calcite vein. Okay, now I'm going to switch it and I'm going to say, here's my rock. Here's my fault. And here's my veins. Okay. Do you agree? Okay, that's what we see. Yes. Like this way? No, still. I have to think about it just a minute. No, I think it still works. Let's draw it. Okay. Now it looks like a ghost. Okay. Okay. So that's the other way you're talking about. Let's go through all of them, okay? So which one is the hanging wall? Left. Which one is the foot wall? Right. Has to be. Which one moved up? The foot wall. So it goes like this. This is a normal fault. Okay, let's do this one. Okay. I don't know if this one works because I've never looked at it from this perspective. So let's figure it out. Okay, which one is the foot wall? And no, hold on. Yeah. No, the hanging wall. If you were to split this apart into two pieces, which one would you hang off of and which one would you walk on? Right? Okay, all right. And in this case, can you really say one moved up? In this case, but then you have to look at it like this. Okay, tell me why the foot wall's on top. Yeah, the foot wall should always be the same. Hold on. I'm gonna figure this out. So wait, so it was like this, and then we do this. Yeah, I guess it does matter. I was thinking like it doesn't matter if you do it 180 degrees difference from each other, but I guess if you do it 90. Yeah, you're looking at it from the different perspective. You're looking at it 90 degrees. So fine, next time I'm going to have to tell everybody, look at it this way and not look at it this way. Okay, with that was what was confusing people? Or most of you were like, no, I didn't even think about that part. Okay, so if we do it upside down 180 degrees, if we do it upside down, then which one's the hanging wall? Left, whoops, hanging wall, foot wall. And then what happened? The foot wall moved up, relative to the hanging. Yep. So this is from our mountains. Our mountains are what kind of fault? It's a normal fault. So what's happening here? I want you guys all to picture in your minds. When it looks like a ghost, it's not the right way then. Okay, so what I want you to picture in your minds is what the way this area looked 50 million years ago, okay? And this area looked like this 50 million years ago, okay? And we had all these cool layers of rocks, but we couldn't see any of them because it was perfectly flat and really boring, okay? It was a high plateau, all right? That's what this area was, okay? And then over the next 50 million years and continuing today, we actually now have a place that looks like this. Okay. So where did our mountains come from? Our mountains came from a normal fault. Okay, that's why we have our mountains here. Our mountains, we live at the base of this huge mountain, and it is all there because of fault movement, normal fault movement, okay? With the footwall going up relative to the hanging wall. And the cool thing is that this is still continuing. So every single earthquake that we have in this area actually pops these suckers up a little bit more. And there's also some creep on it, some really good pressure on it. And this means that we could have a much larger earthquake sometime in the future. Now we will talk about all of this, all of the earthquake stuff and living here on the base of this, of the Wasatch Fault. We'll talk about that when we around Thanksgiving, because we actually have a whole lecture talking about earthquakes. We have a couple of lectures talking about earthquakes. But that is what creates our mountains. So if you think about how tall Temp is, 11,000 something feet, and then it actually is just that much or more below us, several miles down, is the same rock. So we're talking about a huge amount of movement that has created our mountains, and that's why they're so cool. All right, thanks for your attention. Wow, thanks for your attention. Have a great day. I'll see you guys on Wednesday.
I've never come back before.